This lesson is about two kinds of segments in triangles that are new. We have already talked about angle bisectors and perpendicular bisectors. In this lesson, we'll be focusing on medians and then altitudes. So first of all, definition of a median. A median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So see how those markings are showing you on the picture that it's hitting a midpoint at D. The segment that you draw from point A to that midpoint, from the vertex to that midpoint, is called a median. Now you could do that on all three sides. So again, since there are three sides, you would find a midpoint of a side and then draw from the opposite vertex to that midpoint. And you could do that on all the sides. So if you found the midpoint of segment AC, then you could draw from the opposite vertex to that midpoint to find the third median. Now, as you see in the next picture down here, the medians of a triangle are concurrent at a point that's called the centroid. So this point right here, where all of the medians intersect each other. Remember, concurrent means they all hit at one single point. That point right there, if you started with medians, it's called the centroid. Remember that with perpendicular bisectors, it was called a circumcenter. For angle bisectors, it was called an incenter. For medians, the point of concurrency is called the centroid. So every one of these segments has something special about them. The circumcenter gave you a circumscribed circle. The incenter gave you an inscribed circle. The thing that's special about the centroid is every median is cut into a certain ratio by the centroid. So if you look at any one of these segments here, the ratio of the short one to the long one is a 1:2 ratio. So if you look for specifically here, if you look at the median that goes from the midpoint of segment DF to the opposite vertex E, if this little segment right here were 9, then the other segment is going to be double that, it's 18. So the ratio is a 2-to-1 ratio, which means that because it's 2-to-1, since this one's twice as long as that one, the total would be 3, right? It's cutting into thirds, so it's a 1/3, 2/3 ratio. So if you compare the little ones, it's a 2-to-1. If you compare the little one to the whole thing, this is a 1:3 ratio, and then the other one to the whole thing is a 2:3 ratio. So that means that in the picture, if you look at segment DJ, let's say that the segment DJ was 15. So if segment DJ was 15, that's the segment right here, it's cut into a 1/3, 2/3 ratio, or a 2-to-1 if you're comparing the small parts. So if you take 15 and divide it by 3, you'll find the little piece is 5. And then the longer segment is 10, because again, this is 15 divided by 3, or a third of 15. So 1/3 of 15 is 5. And then I usually will just double the little one to get the big one. So 15 divided by 3 is 5. If you multiply that by 2, you'll get the longer segment. Okay, and then on the blue median, which is this one, that's segment HF. HF is cut into thirds also, where again the short segment is 1/3 of the whole, and the longer segment is 2/3 of the whole, which makes the small one and the medium one equal to a 1:2 ratio. So if you are given the small one is 7, if you multiply that by 2, you'll get the 14. Okay, and then if you multiply it by 3, you'll get the length of the whole thing, which is 21. So again, the ratio here, the ratio of these numbers should be a 1:2 ratio, And you can also get the 21 here by adding together those smaller segments. So obviously 7 and 14 added together will also give you 21. And then lastly, we have the median, which is GE. And for that one, they're giving you CE, which is the longer of the two segments. So for that one, the longer of the two is 18. That means you can divide that by 2 to get the short one, which is 9. And if the short one's 9, then if you multiply that by 3, you'll get 27. Now again, also you can get 27 by doing 18 plus 9. That will also give you 27. So here is a summary about the facts of a centroid. So the one we just talked about is the fact that a centroid is dividing the medians into a 2-to-1 ratio. So the big segment to the small segment's 2-to-1. The whole entire median to the other two segments is a 3-to-2 and a 3-to-1 ratio. So every median is divided into a 2-to-1. The second thing is that the centroid is what's called the balancing point of the triangle. You can kind of remember that because centroid sounds like center. So if you were going to balance a triangular plate on your finger, or maybe suspend a triangular sculpture from the ceiling or off of the floor, the point that you would want to use is the centroid. So you would start with the triangle, draw the medians, figure out where the point of concurrency is, and that would be the point where you would balance the triangle from. And because it's a balancing point, obviously you can't balance something that's not inside of a triangle, so the balancing point is always inside, so the centroid is always inside. It doesn't move around. Some of the other segments, like for example the perpendicular bisectors that gave you the circumcenter, that could move from inside on or outside the triangle depending on the kind of triangle. Centroid is always inside. And then lastly, here's a formula for calculating the centroid. So if you know the 3 vertices of the centroid, then it's kind of like a midpoint type of idea, but this time you're sort of finding a point that's in a way the average of the 3 vertices. So if the x1, x2, and x3 are the vertices, the centroid can be found by adding the x's and dividing by 3 for the x coordinate, and adding the y's and dividing by 3 for the y coordinate. Again, same idea as a midpoint. So that's what's happening down here in this problem. On the picture, it says find the coordinates of the centroid. So on the picture, I've kind of done it 2 different ways. So you can see that in the diagram, I have found the midpoint of each of the sides and drawn in the medians. So I'm just looking at it, figuring out where the midpoint would be and drawing in the medians, and then that point of concurrency there in the middle, that's your centroid. So that means it's at the point 5, 3. But another easy way to do it is to use the formula. Okay, so we're using the x coordinates of the vertices. So 1, 9, and 5 are being added together and divided by 3. And then 7, the y coordinates, 7, 1, and 1 are being added together and divided by 3. When you simplify that, you'll end up with your centroid coordinates of 5, 3. Okay, and then the next example, it says which segment is a median? Well, remember, a median has to go between a vertex and the opposite midpoint. So you see some midpoints there, but only one of those segments goes from a vertex to the opposite midpoint. So that midpoint right there to a vertex, segment AD is the median. Remember that a mid-segment goes between 2 midpoints of sides, so that segment, EG, is a mid-segment. And what we're going to talk about in the next portion of this video is that segment CF is an altitude. So an altitude is like the height of the triangle. An altitude goes from a vertex and makes a right angle with the opposite side. So it goes through point C and makes a right angle is perpendicular to the opposite segment. That's called an altitude. So here's definition of altitude. An altitude of a triangle is the perpendicular segment that goes from a vertex of the triangle to the line containing the opposite side or to the opposite side. So it really is, again, just the height of the triangle. It's the same thing as saying the height. Okay, so when you're looking at this obtuse triangle over here, you're going from the vertex and making a right angle with the opposite side of the triangle. So an altitude can be inside, outside, or on the triangle. It depends on the kind of triangle that you're looking at. So for example, if you were drawing the altitude from B to the opposite side AC, because that's an obtuse angle, we have to stretch that out a little bit, and the altitude would actually lie outside of the triangle. Now it turns out that the altitudes are also concurrent, so all four of those segments that we've talked about, when you draw the three of those segments in the triangle, each one of them has a point of concurrency. So for the altitudes, the point of concurrency is called the orthocenter. So as you see down here in the picture, we have the three altitudes drawn. So we've got from a vertex perpendicular to the opposite side, from a vertex perpendicular to the opposite side, and from a vertex perpendicular to the opposite side. So that green point right there for that acute triangle, that green point is the orthocenter, and it's inside of the triangle. On a right triangle, we've got from a vertex perpendicular to the opposite side, but because it's a right triangle, when you come from this vertex perpendicular to the opposite side, that's actually a leg of the triangle. And same thing over here. If you go from the vertex perpendicular to the opposite side, it's actually also a leg of the triangle. So the point of intersection that you see there is actually on the vertex of the right angle. So in a right triangle, the orthocenter will be on the triangle at the vertex of the right angle. And then lastly, the one's a little bit harder to see is the obtuse triangle. So the original triangle there, you want to color that in, make that highlighted so you can kind of see what's happening, and I called those vertices A, B, and C. So in that picture, if we go from vertex C perpendicular to the opposite side and stretch it out, there's an altitude. And then if we go from point A and make it perpendicular to the opposite side here, we're going to stretch out that segment because perpendicular to the opposite side is actually outside of the triangle. So that segment CB has to be extended. And then lastly, from point B, perpendicular to the opposite side AC, well, AC is not quite long enough, so again, we just stretch that out so we can make a right angle from that one. And the point of concurrency that you see there is outside of the triangle whenever it's an obtuse triangle. So while the centroid is always inside the triangle, for the orthocenter, and then it was also true about the circumcenter, the orthocenter can be inside, on, or outside of the triangle, depending on the kind of triangle that it is. And then a few more examples here. A median, remember median goes from a vertex to the opposite midpoint. So there's a median, which we had to verify that that really was a midpoint. And then altitude goes from a vertex perpendicular to the opposite side. So from C to F, because you see that right angle mark there, you know that segment CF is an altitude. So in the picture down here, you have some examples. Because it tells you that that's an incenter, those should be angle bisectors, which you can see because all of the angles are being bisected, and the incenter is the point of concurrency of the angle bisectors. In the second triangle, we have an orthocenter, which orthocenter goes along with the altitudes, and you can verify that because each of those is a vertex to the perpendicular to the opposite side. So the orthocenter is the intersection point, the point of concurrency of the altitudes. Medians, their point of concurrency is called the centroid, and these are medians because they go from a vertex to the opposite midpoint, vertex to opposite midpoint, vertex to opposite midpoint. The medians are concurrent at the point called the centroid. And then lastly, perpendicular bisectors. So perpendicular bisectors, their point of concurrency is called the circumcenter, that you can see on the picture there. It's that point of concurrency right there. And so on this triangle, we can tell those are perpendicular bisectors because of the right angle mark, and the congruent segments there shows you the midpoint. So through the midpoint, perpendicular to that side, and through the midpoint perpendicular to that side at its midpoint. And then lastly, I just have a few little sketches drawn here. I think it's helpful maybe to understand the definitions by thinking about them as each one of them sort of has two properties. So given a triangle, if you're doing a perpendicular bisector, it has to do two things. It has to make a right angle, the perpendicular part, and it has to hit a midpoint, the bisector part. An angle bisector obviously makes two congruent angles, but it also has to go through a vertex. So it's doing two things, going through a vertex and cutting the angle to two congruent parts. A median. A median does two things. It goes from a vertex and it goes to the opposite midpoint. So you need to be looking for those congruent segments there so you can tell that it really is a midpoint. But again, it has to go through a vertex. That's different than the perpendicular bisector because a perpendicular bisector has to make a right angle and it doesn't have to go through a vertex. And then lastly, the altitude is going to go through a vertex. It's going to make a right angle with the opposite side. So it doesn't have to hit a midpoint. It does have to make a right angle, and it also must go through a vertex, unlike the perpendicular bisector. So maybe that's helpful in remembering the definitions. Each one of those things has to have two different properties. And this is the end of the lesson on medians and altitudes.